Hi everyone, Timothy Ferris here with a few words about what I'll call a source and a sink. It's a term borrowed from electrical engineering. I thought I would apply it to the broader range of processes by which we see nature turning relatively simple structures into more complex structures. And this involves essentially three components. First, a source of energy. Second, an environment in which it is possible for that energy to be used to build a more complex structure, whether through living things or through applications like human technology. And by a sink, I mean an ability to drain away the excess energy and the scraps really left over from the construction process, whether natural or, as we tend to say, artificial. And I'd like to briefly look at this process in three environments: the sun and the earth and its molten core, and in the expanding universe as a whole. Let's start with the simplest system, that of the sun and the earth. The sun, of course, is the energy source. Sunlight strikes the earth, warms the surface of the earth. Some of that sunlight is re-emitted as warmth, infrared light technically, from the surface of the earth. The atmosphere is transparent to the sunlight coming in. We can't see the infrared light that comes back off the surface, and some of that heat is trapped by what are called greenhouse gases like carbon dioxide and water vapor in the atmosphere. And this combination of direct sunlight and the reflected heat that's then kept in the Earth's atmosphere by greenhouse gases is what keeps our planet warm. So when we say that it's been possible for life to form and to evolve on the surface of the Earth, what we mean in part is that the surface of the Earth is a place in which energy can come in this case from sunlight, that there is an environment stable enough for more complicated structures to form, and yet dynamic enough for natural selection and evolution to proceed. And in this model, the excessive heat of the process is carried off into space. Global warming, about which there's so much current concern, is caused by burning fossil fuels and injecting additional greenhouse gases into Earth's atmosphere, so that the Earth is trapping more heat than it did in the past, and that's bringing up the temperature of our planet. Global warming is sometimes talked about as if it were some sort of exotic scientific hypothesis, but it's really just basic planetology. If it weren't for the greenhouse effect, the Earth would not be anywhere near as warm as it is. And by adding to greenhouse gases substantially, we are artificially heating the Earth to higher temperatures than it was before. The concept of a source and a sink is useful also in evaluating the idea of Dyson spheres. These were proposed by the physicist Freeman Dyson, who argued that since a star is the primary source of energy for any planet orbiting that star, and since any civilization expanding on into its planetary system would want to make maximum use of starlight, which otherwise just bleeds off into space, we would expect advanced civilizations to build structures that encompass the star. They wouldn't have to close it in altogether, but you could think of it as being gigantic rings, one after another, built over long periods of advancement, sort of where the orbits of planets might otherwise be, but also at different angles that have nothing to do with planetary orbits. The purpose of these rings would be to capture, in the case of our system, sunlight, and to use the energy. As civilization proceeded, these Dyson spheres would become more and more like solid spheres, and on their interiors would be all the vast engineering that was going on in this putative civilization. What Dyson pointed out is that such a process has to have not only a source, but a sink, that no matter how advanced the civilization, the entire sphere would heat up and re-radiate that energy in the infrared wavelengths. And he proposed that we could search for signs of extraterrestrial civilizations by looking for these infrared sources that would really be kind of enclosed stars. That may still be a good idea. A little of it's been done, but we don't yet have the technology to really look in detail for such exotic objects, if they exist. So that's the relationship between the Earth and the Sun. Let's talk second about the Earth and its energetic relationship with its own molten core. Here, a bit of history may be helpful. In the 1800s, when steam engines had been under development for generations, a hot field in science, no pun intended, was thermodynamics, changes in heat over time. This had been occasioned by the development of steam engines, which had really kicked off the Industrial Revolution in many ways, and the desire of engineers and industrialists and scientists alike to better understand the nature of thermodynamics. Scientists applied this study to the Earth's hot core. It was well known to science that the Earth had a hot core. If you dig mines deeply enough, the ambient temperature goes up even just going some hundreds of feet down. And of course, everyone was familiar with volcanoes and how molten rock from the interior is pushed up through the Earth's crust and creates these volcanic plumes. So the scientists studying thermodynamics calculated as best they could how long the Earth's core could have remained molten. And the answer they came up with was about 500 million years. Now that's a long time, but it was a short enough time to alarm Charles Darwin, who had come up with his theory of evolution, and who understood perfectly well that 500 million years was nowhere near enough time for life to have begun as a simple single-celled process and to have built up the structures that we see around us today. And Darwin, in a great illustration of scientific integrity, refused to try to paper this over. He went to his grave saying, "I don't understand how this discrepancy can be resolved, but for my evolution theory to be correct, the Earth must be much older." And we know today it is a lot older. The Earth is about 4.5 billion years old. The reason the calculations had produced such shorter results, 500 million years rather than much longer periods required by Darwinian evolution, is that no one yet knew about radioactivity. The existence of radioactive elements had yet to be established. Because the Earth is a radioactive planet, because it incorporated, along with many other materials, radioactive elements, and because many of those elements are heavy and therefore sank to the center of the planet when it was still a molten ball, the core is constantly heated by its own radioactivity, and that's what's enabled the Earth to remain a dynamic living planet, so to speak, a planet supporting life, for all these billions of years. The planet Mars, which has a smaller core, may have been able to support life early on, but the heat of its radioactive materials was not sufficient in that little core to keep the planet dynamic and alive. All the volcanoes you see on Mars date back to the very early history of the planet, and it's unclear whether Mars could sustain life today. The heat of the Earth's core is responsible not just for volcanoes and for the plate tectonics, the movement of continental plates about on the Earth, but also for undersea vents, where some scientists theorize life may have gotten started. Just hot vents coming up at the floor of the ocean and creating an environment where there is a source, hot water, a sink, the surrounding cold ocean, and an area in between where simple structures like molecules could be built up into more complex structures like those of living organisms. In this model, it's important that the area in between the source and the sink, the area where complexity gets built, be stable enough so that higher structures, once they form by chance, have a reasonable likelihood of enduring, but also dynamic enough that the energy flow continues through the system and allows new innovations to keep occurring. It seems unlikely, for instance, that there's life on the surface of Pluto out toward the edge of the solar system. The amount of energy coming to Pluto from the sun and the amount of energy likely to be coming to it from its interior, it's a small object, are very low. So any processes being driven nowadays would be slow and fairly simple. And it's also hard to imagine life and other complexities evolving say, on the surface of the sun, where there's plenty of energy, and there's also an immediately available sink. The energy is flowing out into space. But the heat is so intense that any structure that forms by chance is almost immediately torn apart by the ambient energy in the environment. With that in mind, let's look at our third case, that of the expanding universe. Here, the energy source is kind of surprising because ultimately it's gravity. The force of gravity pulled matter together, even though the universe as a whole was expanding. So that rather than just expand as, say, something like a gas released from a balloon, the universe expanded, but within it, stars and galaxies formed from material that was drawn together by gravity. In relativistic terms, gravity is a product of the shape of space-time, so one might say that a characteristic of the universe we live in, that is to say the part of the universe that we can observe, is that it has a space-time dynamic that permitted stars, planets, and galaxies to form, thus creating trillions of environments where a source and a sink can, in that middle area, encourage the growth of complex systems such as life. So on the cosmic level, in this paradigm, we would say that the source of energy is gravitation. Collapsed matter to form stars, the interiors of stars fired up as nuclear energy produced a source for planets, and that the sink is the expansion itself. Ultimately, super civilizations can build pretty much anything they like and emit as much energy in the process as they're capable of. But the expansion of the universe itself will take care of preventing that heat from ever overheating, say, entire galaxies. And I do expect that there have been civilizations, if intelligent life shows up with any frequency in our universe, that have gone on to do rather large-scale projects. Here on Earth, we've developed a habit, you might say a prejudice, of talking about our limited resources and about the need to live in a sustainable way, meaning not using up resources that eventually we would run out of. And that's an understandable policy on this one planet. But once you get beyond the planet, just to our solar system, for instance, resources become phenomenologically almost infinite. That's because in our galaxy, for instance, no matter what the scale of your engineering project, how much material and energy, space you need to carry it out, you are always, for millions upon millions of years, going to be able to keep expanding your presence out through the galaxy and achieving these goals. Until or unless, of course, you run into someone else's expanding sphere, doing the same thing from another direction. Whatever we and they may be doing in the future, it's this basic dynamic of a source and a sink that will drive the growth of complexity in our hands as it has in the creation of life itself. Thanks for listening. See you next time.